Hello everyone, welcome back to TechSimplifiedTV. I am Munmun and today's marathon edition is all about interconnect in VLSI Physical Design. Interconnects are the true lifeline of every chip. We will start our marathon with the basic of interconnects and then we will move to the delay calculation following different models like RC, Pi, Elmore. Next, we will explore on-chip inductance followed by one of the most important topic in VLSI, that is crosstalk and signal integrity. Finally, we will wrap up the marathon with multi-level metallization and low-K dielectrics, tracing the evolution from aluminum to copper. The final segment brings together the material physical design perspectives of interconnect evolution, highlighting the process innovations. By the end, you will have a complete view of how interconnect impact modern VLSI design. So if you are interested, stay tuned and stay focused till the end of the video. Now let's move to the pointers we will cover in this episode. First, basic of VLSI interconnects. Next, VLSI interconnect, local and global. Third, desirable or expected VLSI interconnect. Next, real or fabricated VLSI interconnect. Then, interconnect parasitics in VLSI, back end of line or BEOL. Resistance and reliability, capacitance and reliability, inductance and reliability, and finally, impact of scaling. So, let's move to the first slide. Basic of VLSI interconnects. In a IC or integrated circuit, active designs and regions are electrically connected to each other to make circuit. When these active regions or devices are isolated, they cannot work as a circuit. So they need to be connected, and that connect is called interconnects. And these interconnection of active regions, when they will perform, they must connect to the outside world through their input and output bonding pads so that we can insert input data and get the desired result from the circuit. So that is the need of interconnects. So active devices and regions in IC are electrically connected to each other to make circuit. They are also connected to the outside world through their input and output on bonding pads. Contacts, vias and interconnects used for such connections. Depending on the position of the electrical connection, we call them as contacts or vias or interconnects. Next, contact is connection to source, drain and poly. This is source to drain. This is the channel region, and this is the contact to the active region. This is the gate region. When the contacts or the electrical connections are directly to the active region like source, drain or poly, we call this contact. Next, via. As we can see in this diagram, this is via. Connections between interconnect levels. This is the metal 1 level, this is metal 2 level. As the technology has progressed, the number of metal layer has increased. Complexity of design has increased. Complexity of connection has increased. So, metal layers has also increased. Between interconnect levels, the connection is called via, and interconnects are separated from each other by dielectric layers. So these are not actually in the vacuum. This area are oxide are there. Dielectric layers separating global interconnect levels are called IMD or intermetal dielectric, or ILD or interlevel dielectrics. These are basically the nomenclature of dielectric layer to separate it from the gate level. Next, vias connect interconnects through these layers. Obviously, as we can see, these are perpendicularly. Metal is running from left to right or in lateral direction, and vias are perpendicular to it. These components are part of metallization or backend or BEOL. We will elaborate this point. It's very important point that BEOL, when chip is fabricated, first the active regions are fabricated, then these are local connects, these are local connections are made, and then after that last come this metallization process. Fabrication of device is known as the FEOL, front end of line. These all metal interconnects making is called back end of line. Chip surface doesn't have enough space for all connections, so vertical interconnects are built. Active regions are laterally fabricated on the chip surface, so on that these connections are built. Number of metal layers increases with IC complexity. Technology is progressing, device numbers are increasing because we want to realize more complex functionality, and number of metal layer also increasing accordingly. Aluminum interconnects were used as the standard for long time in chip making, and it's sometimes still it's used. In the late 90s, chip makers switched to CU because it conducts electricity better than aluminum. CU interconnects improved IC performance and can match transistor scaling. This whole fabrication method and nodes that's followed Moore's law in last few decades to increase the number of transistors in the same area. Device dimension have been scaled. So when device dimension is scaled, obviously these via disconnects, these also have to be scaled. Otherwise, it will be a kind of this kind of structure. If contact is like this wider, make contact with half with the source region, some with the drain region, then it will not get proper connection, or proper signal will not go to the upper level. So obviously the metal layer need to be scaled down along with the devices. So obviously we need a material which can match the transistor scaling. Let's move to the next slide. VLSI interconnects local and global. This is the diagram. Well, there are two types of interconnects. Depending on their position, we call it local and global. Look at this diagram. It will help you to understand. This is the silicon layer. These active regions, they are up to this zone. That is the FEOL, front end of line, and then back end of line, this one. There are three parts: local, intermediate, and global shown, although we will cover it like local and global. Intermediate layer is very small here. The steps to fabricate this active region and these interconnects are completely different. Their position is different, and that's why there are some issues and concerns are there which are also different for these two layers. Local interconnects at the first or lowest level of interconnects. This is the lowest. Local. These are short. They cover short distances. They connect gate sources and drains in MOS technology and emitters, base, and collectors in bipolar technologies. Local interconnects are small and short. Polysilicon, silicide, titanium nitride, tungsten can act as local interconnects. There are many choices for interconnect material. The reason behind is that local interconnects can afford to have higher resistivity since they do not travel very long distances, but they must also be able to withstand higher processing temperature. Now there are two very crucial points. Local interconnects, as we said, they are very small and they run for short distances. If resistivity of a wire is higher, heating can happen. Longer the length of the wire and higher resistive material, then obviously it will resist current more. For local interconnects, we must choose a material which can withstand higher processing temperature. Temperature handling capability of that material with which we are manufacturing these local interconnects is higher, then it can handle higher temperature of fabrication of this process or this area. While we are fabricating all these steps, these metal layers, if metal layer or interconnect layer here will break down, then there is no point of making or doing that, because that's a failed chip. It will not work accordingly. Global interconnects are usually made of aluminum. They are above local interconnects. Obviously, physically we can see they are above local interconnect level. Global interconnects are thick, long, and widely spaced. They often travel over large distances between different devices, different parts of the circuit, and therefore they are always metal with lower resistivity. They run longer distances from one corner to other corner. So if resistivity is higher, that resistivity of the material will resist the current, and also heating will be there. So let's move to the next slide. Now, desirable and expected VLSI interconnects. We have some ideal assumptions like where only connects functional elements and does not affect design performance. It's absolutely wrong. They have a huge impact on design performance or chip performance, and that's why we are discussing this topic today here. A voltage changes at one end appears at the other end without any delay. That is where is an equal potential region. We think that it's instantaneous. That's not. Obviously, a function of time, a function of frequency. These are the basically ideal assumptions. In reality, it doesn't happen. There are a list of desirable properties of interconnects. Low electrical resistivity. It's always good to have lower electrical resistivity. Low capacitance, that is low dielectric constant. For low RC delay, crosstalk power loss. High electromigration resistance. What is electromigration? We will discuss it later. Electromigration is a reliability issue for interconnects. Occurrence of electromigration actually leads to chip failure. Ease of deposition of thin films of the materials. Sometimes we need to deposit thin film of material, so not all material is good for this purpose. So the metal we will use that must have that property, ability to withstand the chemical and high temperatures required in fabrication process. We have already covered this point in previous slide. Stable contact structure. There should not be any kind of chemical reaction with the material with which the metal is going to get connected. Then there is no point, because once a chemical reaction starts, most of the time the resulting material will not be that metal or that material. It will be some other materials. Adherence to insulating films. Silicon dioxide is as an insulator the most choiceable one. Later on many other also have been added in the list. Although silicon dioxide is the most go-to oxide, the adherence should be good to stick to that material. Low internal stress and surface roughness. These are basically chemical properties. When we are manufacturing an IC, it's basically a lot of materials and their chemical properties, and they should stay side by side to make the design work. Next, easily etched using plasma processes. That material can be easily etched using plasma process. Compatibility with all other semiconductor processes. And finally is low cost, because cost is concerned. Next, real or fabricated VLSI interconnects. Now let's see how real or fabricated VLSI interconnects behave in real world. Interconnects have resistance, capacitance and inductance per unit length. Wiring of IC forms a complex geometry that introduces capacitive parasitics, resistive parasitics and inductive parasitics. All the basic rules of electrical networking get applied. A real material has resistance, they have some capacitance and inductance value. A layer of metals, they are separated by dielectric layer and current value is really low. When we consider the dimension of the geometry, flowing current in different nearby two conductor, they impact on each other. What does parasitic do? Increases propagation delay, causing a drop in performance. Impact on energy dissipation and power distribution. If the long interconnects have all these parameters, these resistive, capacitive and inductive value, then obviously current travel from one node to another node, there will be some changes which is not desirable and introduces extra noise, resulting in reliability of the circuit. We need to model the resistive, capacitive and inductive parasitics of wires, and accordingly we must do our checking and steps so that the chip doesn't fail. So what we do, the back end, there are so many reliability steps are there that actually includes this effect of resistive, capacitive and inductive parasitics. So modeling of wire capacitances is a non-trivial task. It's a really tough work. There are two types of capacitance occurring: parallel plate and fringe capacitance. Capacitance of wire is a function of shape, distance and surrounding wires and substrate. The resistance of a wire is proportional to its length and inversely proportional to its cross-section A. We all know that R is equal to rho L by A. Inductance in interconnects is represented by voltage drop due to rate of change of current with time. In earlier days in research, only R and C components used to take in consideration, and later on in high frequency this L component is also considered in doing modeling and all. It's a real tough modeling and very necessary and very crucial. Now, parasitic extraction. That's an important part. Parasitic extraction. There is a file format called SPEF. SPEF. Parasitic values of a circuit. That is written in its IEEE format. Obviously, tool generated, not human written file format. It's written in that file. Standard EDA tool is used to extract parasitic values, and it's a part of backend, part of basically physical design. Parasitic extraction is to calculate the parasitics of wires and create an analog model of the circuit. Extracted parasitics are included in timing power analysis to get more realistic result. When we consider there is no realistic hindrance like resistance, capacitance and inductance, our study is something. And when we include all this delay and all, then performance will be completely different. Before sending the final layout to the fabrication unit, we need to analyze it from all angles so that after fabrication, after putting all the money, it doesn't fail on the realistic world. The chip doesn't fail. Standard parasitic extent format is an IEEE standard for representing parasitic data of wires in a chip in ASCII format. We already have an episode on SPEF file format and its impact and importance all. Link will be given in the description. You can watch it. Now, interconnect parasitics in VLSI. We said that resistive, capacitive and inductive. So this is the resistance. The resistance of a wire is rho L by A area, this cross-sectional area, that height, width. And this is the basic formula we all know. Now let's move to inductance. Inductance of a section of circuit states that a changing current passing through an inductor generates a voltage drop. That voltage drop is proportional to change of current with time. Delta V, or change of that voltage drop, is proportional to di dt. An important source of parasitic inductance is due to bonding wires and chip packages. If that is the circuit, that must be connected to the outer world. So from there, and this connectivity, their inductance value is not very negligible, and in transient and in switching mode, current need to change. That time, that inductance comes into place. Again, interconnect parasitics. Now capacitive. There are two types of like parallel plate capacitance and fringing capacitance. This is parallel plate capacitance. This is substrate dielectric. The simpler model, that is C is proportional to epsilon 0 epsilon RDI, that is the dielectric layer, divided by TDI and then WL. Width and length of the wire, TDI and epsilon DI represent the thickness and dielectric layer and its permittivity. Fringing capacitance is between sidewalls of the wires and the substrate. This is the equation. So when we consider total wire capacitance, so total wire capacitance would be fringing and parallel plate. CPP plus C fringe. This is the total. Now let's move to the next slide. Now back end of line. So let's see what are the steps by which we make these interconnect levels, that back end of line. The back end of line, or BEOL, is a portion of IC fabrication where the wiring is done through metallization or vias, including dielectric separators among various metal layers. BOL steps are like silicidation of polysilicon and source drain diffusion. It starts from there. Then adding a pre-metal dielectric or CMP, processing it. It's a step. Make holes in PMD, pre-metal dielectric, and create contact through it. A pre-metal dielectric is fabricated and then a hole is made through it and contact is done through it. Then add metal layer 1. First metal layer is fabricated. Then add dielectric layer, that is intermetal dielectric. One metal layer is fabricated. Now intermetal dielectric is done. Then through CVD makes vias through IMD. A metal layer is done and then we are adding intermetal dielectric. Suppose it's a metal layer, and now whole area we are oxidation, and now dielectric layer is done. So even if we vertically, if that is the vertical direction, we make another layer of interconnects, we need to connect. There will be a separator, so we have to make hole through it so that this layer and that layer get connected. carry on last 3 steps until all metal layer as per technology node are done. When a technology node is defined, it always the process is optimized. When a fabrication unit release their data regarding one new technology node, they include all the metal layers and everything. Last 3 steps means add metal layer, then add dielectric layer or IMD, and then make CVD and build these vias through IMD. If 7 or 8 metal layer is there, so this process will get repeated for that many times. Then add final passivation layer to protect the chip from weather and outer world. Now BOL corners, that a very important part. What are BOL corners? Back end of line corners. It's part of RC corners or PVT corners, process voltage temperature corners. We have detailed video and articles on that. So link will be given in the description. I'm going to tell here in short, parameters of a semiconductor fabrication are generally statistically distributed because it's not an ideal process. It's a real world. Not all two devices have all the properties same. Some variation occurs in length, width, oxide thickness and all. Since in a wafer, ICs we fabricate, they are not identical. We must judge their merit within a range of data, not a particular one data. Because when a device is very small in dimension, half of nanometer is even crucial factor. For a batch of ICs, we define basically a range of values. And these are some corners like this extreme values. Some value comes from BOL steps also. These are basically C worst, C best, CC worst, RC best, RC worst. In detail, you can read the articles or watch the video. So let's move to the next slide. The impact of parasitics. Now resistance and reliability. Electromigration. In operating condition, a chip may go above 100 degrees Celsius during practical operation. High frequency power loss and consequent heat dissipation contributes in increased temperature. Since the interconnects have resistive properties, so heat dissipation is always there. Continuously, the temperature of the chip increases and rise in temperature enhances solid state metal ion diffusion. It's basically material level performance. So electromigration is caused by scattering of moving electrons with the ions, that is by momentum transfer between electrons and ions in metal interconnects. While in operation, chip temperature increases depending on how long it's open to that situation. The moving electrons within the interconnects, they scatter the ions or the metal molecules. So momentum transfer happens between electrons and ions in metal interconnects, and this ion-electron interaction is sometimes referred to as electron wind. This causes the wire to break or to short circuit to another wire. Such situation create void in interconnects that can lead to open circuit. If ions from this zone is moved, either there will be a void, and if it's moving to and getting to another wire, so it's basically doing the short between these two. In both the cases, the electron flow or the current flow will not be in the desired direction and chip will fail. EM is one of the most menacing and persistent threat to interconnect reliability. So these are some pictures. As you can see, there is a void in via. The electron is traveling and you can see this zone, right? Metal layer has, if it's go a little bit more, it will touch it and there will be a short. There is no point. This black dark area is basically in intermetal dielectric, but this electromigration process is doing that. Look, it's connecting. So here it's creating an open circuit. Here it's almost going to make a short circuit. So in both the cases, the chip will fail. And we have 3 episodes on electromigration. Link provided in description. Now, ohmic voltage drop. Current flowing through a real wire results in an ohmic voltage drop that degrades the signal levels. It's a real wire, so ohmic voltage drop will be there and degrades the signal level. Chips are basically operated at lower voltage level. Even from that, if some voltage get dropped at the interconnects, at the destination, the voltage level degraded. If it drops below the driving current of a system at the destination, the device will not perform accordingly. Suppose there is a signal is traveling a longer path from here to here. This is a block, that is a block. here block 1 and that is block 2. So if this length is longer enough and voltage drop is enough, when the signal travels from here to there will be a significant amount of voltage loss. And if it very higher, then sometimes it may happen that the reaching voltage of signal just fall below the switching value of components here present here. So desirable performance we are not going to get there. The affected value of voltage reduces noise margin and changes the logic level as function of the distance from supply terminals. As the distance changes, how much voltage is getting dropped there, the voltage margin level gets changed, and that change all the thing. Higher drops on supply network also impact the performance of the system. A small drop in supply voltage may cause a significant increase in delay. These are the effects. Now RC delay. Signal doesn't travel instantaneously in wires, and that wires and delay of wire grows quadratically with its length. So length increases, delay also increases with that. The signal delay of long wire is dominated by RC effect. This is becoming even bigger problem in modern technology, because we said the more the technology is advancing, length of interconnect is increasing and layer of metal layer has increased. This leads to situations that take multiple clock cycles to get signal from one side of a chip to its opposite end. Its delay becomes so much, multiple clock cycles required to reach a signal from one corner to another corner. Next, capacitance and reliability. In real world of IC, each wire is coupled to both grounded substrate and also to the neighboring wires on some layer and on adjacent layers. Through via the layer of interconnects are connected to each other. It's not completely isolated. So some capacitive components connect to other wires with dynamically varying voltage. Capacitive components, they are connected to other wires where the voltage level changes. So effect of that change have some impact on the capacitive components also. And such variable or floating capacitor causes crosstalk and a negative effect to the circuit. This varying capacitance value have a deep impact on the circuit performance. Delay in the signal transmission through wire is proportional to the capacitance charged. And more capacitance means more dynamic power. Coupling capacitance is an increasing source of noise and make delay estimation hard. This coupling capacitance, it's an increasing source of noise and makes delay estimation really hard. In a practical situation, a wire is surrounded by wires from other sides and in between dielectric layers. So many parallel plate capacitors in all sides, and they all are within ambience of IMD. When we take the whole picture, it's a very complex model. Even if all the capacitance have smaller contribution, the overall contribution, and even with changing voltage, switching effect is happening, voltage level is changing, because we are not designing a system for keeping it idle. It will work. Voltage level will go up and down accordingly. Our design, when the total picture is there, it's a tough thing to calculate. What are the steps we can take to reduce interconnect capacitance? Use of low K dielectric, which reduces permittivity and hence capacitance. Low K means lower than silicon dioxide, and in high K we consider it as compared to silicon dioxide, because for many years silicon dioxide has been considered as the golden one. Increase the spacing between wires. We are downsizing the transistor dimension. When we are trying to adjust more devices in an IC or in a wafer, at that time increasing spacing is not always possible. Separating two signals with a power or ground line acting as shield, that might be a method. Use minimum wire width wherever possible, which in turn will increase the resistance. R equal to rho L by A. So in denominator there is A. A means height into width. So if width they are decreasing, so R value will be increased and then the ohmic effects will be higher. So we have to choose between these two. It's a trade-off. Now let's move to the next slide. Now crosstalk. It occurs due to unwanted coupling from neighboring signal wire to a network node. The resulting disturbance acts as noise source. It's not desired. Here unwanted voltage interference is basically noise. Capacitive crosstalk is the dominant effect at current switching speed. Potential impact of capacitive crosstalk is influenced by impedance of the line under examination. The design functionality and its performance can be limited by noise. The noise impact can limit the frequency of operation of design, and it can cause functional failures. Crosstalk may lead to setup or hold violation. Setup or hold violation, basically two major timing violation taken care in backend timing. Then propagation delay. Capacitive crosstalk may result in data-dependent variation of propagation delay. Coupling capacitance is a large function of overall capacitance in the dense wire structure of advanced technology node. This increase in capacitance is substantial and has a major impact on propagation delay of the circuit. Inductance and reliability. Inductance with LDIdt voltage drop. During each switching action, a transient current is sourced from or sunk into the supply rails to charge or discharge the circuit capacitances. In our basic circuit analysis, we have studied that the transient effect happens during the switching. Here also, transistors or MOSFETs are basically used at switch. So when signal switches from 0 to 1 or 1 to 0, transient current is sourced from or sunk into the supply rails to charge or discharge the circuit capacitances. So with that transient current actually either charge or discharge the circuit capacitances. Both VDD and VSS connections are routed to the external supplies through bonding wires and package pins and possesses a non-ignorable series inductance. That bonding wires, VDD and VSS, finally they are connected to bonding wires. They are supplied from outside. Change in transient current leads to large current surges. That's not negligible. And then transmission line effects. When an interconnect becomes sufficiently long or when the circuits become sufficiently fast, the inductance of wire starts to dominate delay behavior and transmission line effects become significant. So actually the change of current, rate of change of current, that is getting resisted by the parasitics, and that is become very crucial when the wire becomes sufficiently long. So if long, it takes a longer time, so effect will be more. Now, impact of scaling. Scaling is basically downsizing the device dimension. We have followed Moore's law and downsized the device dimension or MOSFET dimension and packed more devices into the same area. But that has impact on interconnects also. Here we will, in this slide, we will discuss that. Dimension of interconnect scaled down by a factor calling scaling factor. It's not abruptly changed. It's changed with a factor that is called scaling factor S. And this scaling factor is an integer. The resistance, capacitance and inductance are affected by scaling because all are function of that length, height and width. Wires, there are two types of wires, short and long. Short wires are typically used for local communication between gates, local interconnects, and long wires are used for long range communication at the different corners of IC. There is a table for full level scaling, short wires and long wires, and R value change with a factor of 1 by S, scaling factor. And long wires, it's 1 by S square. For C, for short wires, it's S, and long wires, it's scaled by factor 1. That's same, remains same. RC delay, these are the values. And scaling with thickness, keeping thickness constant, the value will be different. So we can see that with scaling, the value get changed. So if we compare this RC value, RC delay value over two different technology nodes, they will be different. So that's the impact of scaling. So that we all had for today's episode. We will discuss delay models and their calculations in a later episode. Now let's take a look at the pointers we are going to discuss in today's episode. First, delay in IC. Second, delay models. Then lumped C model. Then lumped RC model. Next, pi and T models. Next, Elmore delay model, then RC tree network with Elmore delay, RC chain with Elmore delay model, distributed RC line model, transmission line model, and lossless transmission line model. So let's move to the first slide. Delay in IC. Input to output delay in IC has two components, gate and interconnect delay. In previous episode, we have discussed about delays, that when signal is applied at the input of the IC, it takes some finite time to get the desired output, expected desired output at the output pin of the IC. So that is the delay, input to output delay for an IC. And this delay in IC has two components, one due to gate or cell, and another component of this delay is contributed by interconnect. We call it interconnect or wire delay. First, gate delay. Signal transmission through a gate is not instantaneous. That even signal transmission, this is a NOT gate, input of this NOT gate, and get the desired output. We don't get that instantaneously. It takes finite time shift. When this 1 to 0 transition is happening, the desired output should be 0 to 1 transition, and we get it, although after some time delay. That is gate delay. The time required for signal to travel from input of the gate to output of the gate is gate delay or propagation delay. We also call it propagation delay. The figure shows gate or propagation delay of a NOT gate. Output changes after a delay of delta with change in input. As we can see, gate delay is not equal for high to low and low to high transition. This high to low or low to high transition, the delay is not exactly same. We will discuss it in some later episode. Today, we will mostly concentrate on wire delay or interconnect delay. Now, let's move to wire delay. So, wire delay interconnects or wires connecting active devices at delay while carrying signal. This is wire delay. So, between two gates, there is gate 1 and there is gate 2. They are connected by wire. So when signal is applied here, we get desired output, but the desired output will not reflect or will not reach from this point to that point instantaneously. We know why. Because of interconnects add delay because of their parasitic effects. So there is a finite time, and that finite time is denoted by this delta. That is the wire delay. Wire delay is also known as transport or flight delay. Wire delay becomes dominating with higher operating frequency, that is lower device dimension. Now that is a table. In mid-80s, gate delay was 85% and 50% of the total delay was contributed by wire delay. While we have moved to more small devices in mid-90s, the ratio became 50-50. Now post-millennium, the situation has worsened so much that gate delay or cell delay only contributes 20% of the whole delay, whereas 80% comes from this wire delay. So, although we have today discussed this gate delay, what is gate delay and wire delay, we will mostly concentrate our today's episode on wire delay. So, let's move to the next slide. Delay models. We have already discussed about cell or gate delay and wire or interconnect delay. So, let's know the name of the delay models. NLDM, ECS and CCS. These are delay models for gate or cell delay. And for wire or interconnect delay, we use lumped C model, lumped RC model, distributed RC model, transmission line model, wire load model. Now, NLDM is nonlinear delay model, ECS is effective current source model, CCS is composite current source model. These all delay models and their data all are usually get mentioned in leaf file. We have episodes on characterization. Link is provided in the description. Watch the episode. You will get better and clearer idea about all these models. So since today's episode is concentrated on wire or interconnect delay, it's just what I'm doing is just touch base for these names and all, but actually we will discuss in detail about these models. RC network and gate delay modeling. RC circuits are frequently used to model the timing characteristics of ICs. Here also we will talk a little bit about gate delay modeling because of this RC network. Why RC network? In coming few slides, we will discuss in detail about RC network and delay modeling. So here we are just giving you an idea why RC network. In gate delay modeling also we use RC network. RC circuits are frequently used to model timing characteristics of ICs. When one logic gate drives another gate, the input circuit of the second gate can be modeled as an RC load. For electrical modeling, we do the approximation of the active devices as passive device and then do the calculation. The propagation delay through the first gate is calculated by assuming V in as ideal square wave and the RC load. These models we just try to be as close as possible to the real-time scenario. This works really well for EDA tool and design purpose. Gate delay is inversely proportional to the switching speed of the gate. So obviously, if delay is high, or it will take a lot of time. If delay is less, though, the gate will switch quickly. Next, RC network and wire delay modeling. A wire can be modeled as many cascaded sections of simple RC circuits. When a square wave is applied to one end of the bus, it takes time to propagate. This delay time due to wear can be calculated based on value of R and C in each section and number of sections used to model the wear. The longer the wear, the more sections are needed for accurate model. Now, why RC network is important? It gives us a good approximation of a long wear. A wear can be modeled as a many cascaded section. So first, what actually we do, we take a smaller model of RC and keep on repeating that thing again and again and again. When square wave is applied to one end of the bus, it takes time to propagate because of delay. Obviously, the delay time due to wear can be calculated based on values of R and C in each section. So we break it in smaller section and calculate and then do the summation. We will see it later. The process, this is the basic process. And the number of sections used to model the wear. So if the number of sections of such RC basic structure sections are more, the result will be bigger number. So delay will be more. The longer the wear, the more sections are needed for accurate model. Now, wear load model, we said that wear load model is used to estimate delay based on area and fan out. Semiconductor vendors develop wear load models used in pre-layout design cycle. So here we will not consider wear load model in our discussion in detail. Whatever timing model and estimation we are discussing today, this is completely for post-layout design cycle, that is PD. Wear load model we will discuss in some other episode because that is not part of physical design. So let's move to the next slide. Now, lumped C model. Circuit parasitics of a wire are distributed along its length and are not lumped into a single position. So at every point, when a signal travels from one point to other, it faces effect of parasitic at each point. Although for our ease of work, we adopt some model. One of them is lumped C model. Although we know that is the parasitic is not lumped into a single position, but still we follow such rule for ease of calculation. Lumped model is considered in a circuit where single parasitic component is dominant. If a single parasitic is dominant, in many cases in maths we do it keeping one parameter, tending it to 0. So we keep one parameter off there so that the calculations become easier. Interaction between the components is small. And third, one aspect of the circuit behavior is considered. We are considering single parasitic component is dominant, others are not. Interaction between components is small. One aspect of the circuit. So when which one is predominant, we will consider that one and accordingly we will model. This is the driver. This is V out and that happens on the higher node, more matured node. Capacitive action is more predominant compared to the resistive parasitic. So there we can approximate that there is no resistance, only capacitive actions are there. That is modeled by some capacitance. So this is the driver and this is the V out. So that scenario is modeled as this is the signal. Then when it's on, we consider it as a resistor, and altogether all capacitance are lumped, their values are lumped into one, and that is the V out. This is the easiest or the simplistic model. Effects of parasitic can be described by an ordinary differential equation. That's one point. If parasitic R is negligible and circuit is operating in low to medium range, only capacitive component is considered. Distributed capacitance lumped into single capacitor. There is a condition that it's operating in low to medium range. And resistance is negligible if the technology node is on the matured side. That is lumped C model, suited well for older technology node where wires were wide. High cross-sectional area A means less R. So resistance is not that dominant. In this model, where is equipotential region and where does not introduce any delay due to resistance. Impact on performance is introduced by loading effect of the capacitor on the driving gate. This capacitive lump model is simple and effective. Model of choice for analysis of most interconnect wires in older techno. For older technology nodes or matured old technology nodes, this is the most choiceable model. Now let's move to the next slide. Lumped RC model. Lumped RC model is used when wire length L is greater than few millimeter and resistive component is considerable. With scaling, where cross section is reduced and R become considerable. Lumped C model is inadequate because the assumption for lumped C model was that R is less. If R is increasing, then R is also becoming a considerable and dominant factor. So we cannot use lumped C model there. Now interconnect is modeled with resistive, capacitive or RC model. Multiple approaches are there depending on complexity and operating condition of the circuit and verified with accuracy of the result. For lumped RC model, there are multiple approaches depending on the complexity and operating condition. And now lumped RC model, the total resistance of each wire segment is lumped into one single R and global capacitive is combined into single capacitor C. Within driver and receiver, this is the model. Total resistance of each wire segment is lumped into one single R and global capacitance is combined into single capacitor C. Again, approximation, although they work really well, this model is pessimistic and inaccurate for long interconnect wires, which are more accurately represented by distributed RC model. If its interconnect wires are really long, then more accurate model is presented by distributed RC model. So next slide, RC networks. Studying lumped RC network is important as the distributed RC model is complex and no closed form solution exists. Distributed RC model is a better approximation, although they don't have any closed solution and solving is complex. The behavior of the distributed RC line can be adequately modeled by a simple RC network. So when the model is accurate, although solving it a complex situation, we go for another approximation. So we approximate it as simple RC network and then try to find the solution. A common practice in the study of the transient behavior of complex transistor wire network is to reduce the circuit to an RC network. We reduce them to a simple RC network. Analyzing such a network effectively and to predict its first order response is important for designers. We try to keep the answers simple. So we try to predict the first order response of the system. Two popular network are tree network and RC chain or ladder network. This is the tree network. This one. This is S or input node. From there, at each node, they are grounded by a capacitor. And this is a ladder or chain structure. These two networks are popularly used in modeling. Now let's move to the next slide. Pi and T models. The distributed RC delay can be modeled by breaking up a wire into one or more segments and using lumped model for each segment. Getting solution to distributed RC delay model is complex and tough, so we approximate it by simpler form of RC network. What we do that we break up a wire into one or more segment and using lumped model for each segment. Next, popular lumped models are Pi and T models, named obviously after their shape. There is another model, L model, which is not really good approximation. That's why we have not included it here. R and C depend on length of the segment. We are breaking the wire in smaller segment, and for each segment we are applying that lumped RC. So resistance and capacitance of that segment is lumped into single R and single C, and then it become a network of series of R and C. So value of R and C depend on length of the segment. More the segment value keep on adding. Pi and T model are both good models, although Pi model is slightly more convenient because of fewer circuit nodes. Most circuit simulators have built-in distributed RC model of high accuracy. So these models are, everything is included in circuit simulators. The Pi model, Pi 2 model, Pi 3 model, as we can see, T2, T3 model, these are models, popular models. So let's move to the next slide, Elmore delay model. Elmore delay model is derived originally in 40s for circuit applications and applied in 80s for RC trees. Elmore defined delay through linear network as the first moment of network impulse response. It gives the first order solution. The Elmore delay formulas are immensely useful and simple model, easy to use model. Layout people use in algorithms single time constant. The solution we get is basically single time constant solution and more accurate compared to simple length based scheme. Although it's not super accurate, it requires some later verification with higher order model that incorporate more than one time constant. Simple RC model provides general approximation of timing behavior of digital integrated circuits. Elmore delay model is used in order to improve accuracy of RC model. So RC model provides general approximation of timing behavior of a digital IC. Elmore delay model is used to improve the accuracy. We need to be closer, as much as closer possible to the real-time scenario. Here the RC segments made up of series resistance Rn and capacitance Cn are created. Think of current like real water flowing in tree. This is current in, this branching out. It's a tree-like structure, main branch, then smaller branch, then going towards leaf. From any component of tree looking at the source, it's upstream, and look towards leaves, it's downstream. So next, RC tree network with Elmore delay. Now we will apply Elmore delay on RC tree network to get the result. Wire branching into many destination modeled as RC tree. A wire branching into many destination like this, we model it with RC tree. It's a tree of resistors obviously. Root of the tree is at source node S, where input signal is applied. There is no loop. At the branch end, output is measured. Each intermediate node is grounded with a capacitor. As we can see, there exists a unique resistive path between the source nodes and any node I of the network. There is an unique resistive path between any node and the source node. Like S and 2, the path is this. S and 3, path is this. S and 4, R1, R3, R4. And to I, R1, R3, Ri. This is the path. The total resistance along this path is called the path resistance, Rii. The path resistance between the source node and node 4 is expressed as R4. So this is the node 4. So what would be the path resistance? When signal will travel from this point source node to this node 4, they will travel through R1, R3 and R4. The path resistance of the shared path can be expressed as resistance Rik. There are shared path resistance is calculated by a formula that summation of Rj, where k is from 1 to n. Basically, the expression is like this is the expression, and this is effective resistance between the input and node k in common with path between the input and node I. If we want to calculate shared path resistance between two different node k and I, that would be, we have to take effective resistance between the input and node k 1 and effective resistance between input and path I, and we have to take common of these two like this. Rj belongs to path S to I, intersection path S to K, not union, intersection. I hope we all remember the set theory. If that is a set and that is a set, this is the intersection, a common point. So using above formula, Ri4 is R1 plus R3. How it is happening from, so Rs to Ri is R1, R3, Ri. And S to 4 is R1, R3, R4. So common part is R1, R3. That is the shared resistance of these two nodes, 4 and I. Similarly, 2 and I, it's the common resistance is R1. So this is the Ri2 equal to R1. The Elmore delay from source to node I of an RC tree is given by summation of Rki and Ck. Ck capacitor on node K and Rki shared resistance between node K and I. So first calculate this Rki calculated. Now this Elmore delay model for network is R1 C1, R1 C2, R1 plus R3 C4, R1 R3 Ri Ci. This way it goes. So let's move to the next slide. RC chain with Elmore delay model. It's a special case of RC tree network, non-branched RC chain or ladder. In digital circuits, similar structure is found, represents an approximate model of a resistive capacitive where the delay component of node 1 is C1 R1. R1 is the total resistance between node 1 and the source. Node 1 and source, this is the R1 total resistance. And C1 and R1. Then node 2, R1 plus R2. And delay is summation of capacitance I into resistance from source to capacitance I. So if that is the ith capacitance and the ith node, so R1 C1, R1 R2 C2, this way it goes, and that R1 R2 R3, then Ri C1, this way. This gives the right answer for all values of C and R unless these both have equal to 0. Its only equation is that is correct in all the limits. Now let's move to the next slide. Distributed RC line model. Distributed RC line model is more appropriate model. R and C stand for resistance and capacitance per unit length. We know that parasitics are distributed across length. Here the resistance and capacitance are per unit length. The voltage at node I of this network can be determined by solving partial differential equations. C delta L del Vi del T equal to Vi plus minus Vi plus Vi minus 1 minus Vi divided by R del L. By reducing delta L asymptotically to 0, we will assume that delta L tends to 0, and then we will get that RC del V del T is equal to del square V del X2, where V is the voltage at a particular point in the wire and X is the distance between this point and the signal source. These equations are difficult to use for ordinary circuit analysis. The distributed RC line can be approximated by a lumped RC ladder network, which can be easily used in computer aided analysis. So again we are taking different approximations, like first delta L will tend to 0 and then it will become a function of RC, and we will try to approximate it by a lumped RC ladder network because it's easier to solve and then use in computer aided analysis. Let's move to the next slide. Now transmission line model. Inductance is also there. The inductance is distributed over the wire like R and C. A distributed RLC model of wire known as transmission line model becomes most accurate approximation of the actual behavior. In transmission line model, a signal propagates in the interconnection medium as a wave. In the distributed RC model, where the signal diffuses from the source to the destination governed by the diffusion equation, in the wave model, a signal propagates by alternatively transferring energy from electric to the magnetic fields or equivalently from capacitive to inductive modes. So, when we consider RLC, R, L and C, it's a transmission line model. We are considering a point X along the transmission line, as the figure is showing here. At time t, the following set of equation holds. These two equations we get two partial equation, del V del X equal to minus IR minus L del I del T, and del I del X equal to minus GV minus C del V del T. Assuming that leakage conductance G equals to 0, which is true for most insulating material, and eliminating the current I yields the equation. It's reduced to this equation where R, C and L are the resistance, capacitance and inductance per unit length respectively. This transmission model has more parameters and more complex. Let's move to the next slide. Now lossless transmission line. For the lossless transmission line, R is 0 and the previous equation simplifies to ideal wave equation. So R component is also 0, so that is reducing to this equation, and if we apply step input, so that propagates with speed v, which gives a solution of this L and C. Values of both L and C depend on the geometric shape of the wire. Their product is constant and is only a function of surrounding media. The propagation delay per unit wire length of transmission line is the inverse of the speed. So this is the equations for lossless transmission line. Today we will conclude here. So that we all had for today's episode, and today we concentrated only on the delay models for interconnects. We have not included cell delay here. That's altogether a different discussion and we will cover it in some other episode. So let's take a look at the pointers we are going to discuss in today's episode. First, how on-chip inductance becomes significant. Second, interconnect model mapping with technology node, loop and partial inductance, transmission line model, a small recap, dependence of impedance on frequency, impact of on-chip inductance, first, second and third slide, then difficulties with inductance, then techniques to minimize on-chip inductance, first 2 slides, then techniques to minimize on-chip inductance, more 2 slides, and significance of termination, and finally modeling of interconnect at high frequencies. Now let's move to the first slide, how on-chip inductance becomes significant. On-chip inductance effects have become increasingly significant because some global signal and clockware have large widths and thicknesses at the top level of metal to minimize delays. To minimize the delay, some top level metal layers like global signal and clockwares, their widths and thicknesses are kept wide. They have larger widths and thicknesses, so these decrease the resistance of the wires, making their inductive impedance comparable to the resistive part. Now, impedance of metal interconnect is expressed with Z equal to R plus J omega L. If resistive part is less and at increasing frequency, this part is comparable to R. So, when one part of impedance is comparable to the other part, we have to consider the both. We cannot any longer ignore this part. Next, as the clock frequency increases and the rise time decreases, electrical signals comprise more and more high frequency components, making the inductance effects more significant. Clock frequency increasing and electrical signals, they are comprised of more high frequency components, and from this first point, this frequency portion is increasing, so inductance part is increasing, so we cannot ignore inductance effects anymore. And this is a table. It's showing over the years how frequency has increased from 1.25 gigahertz in 1999 to 13.5 gigahertz in 2014. Signal transition times become more shorter comparable to the signal time of flight, and devices become faster. So speed has increased, devices become more, their dimensions have become smaller, their switching speed has increased, so devices become faster and signal transition is becoming faster. With the increase of chip size, it's fairly typical that many were long and run in parallel, which increases the inductive crosstalk and delay. Just look at our smart devices, our consumer electronics. Our device is as smart as much its processor or their processing unit is smart. So we want more and more complex operation in our devices or in our consumer electronic devices. So just to cope up with that, the chips are increasing in size and they are accommodating more and more devices into the same chip. So what is actually happening? The wires or interconnects, they are connecting. There are many operating blocks are there on the same design, same system, and they are connected for complex operation. So wires are running for longer length and they are running in parallel. So that increases the inductive crosstalk and delay. And with the push of performance, some low resistivity metals like copper, they have replaced aluminum in order to minimize the RC delays. That increases inductive effect more because resistance becoming less. So this portion is again becoming more significant compared to R. So that's a point. Now let's move to the next slide. Interconnect model mapping with tech nodes. There is a diagram. It's showing 2 pieces of interconnects, and just to remind us that an interconnect is not just a piece of interconnect or piece of metal. It's basically capacitor, resistor and inductor. So this is the model for the first piece of interconnect, and this is the C2, R2, L2 for the second piece of interconnect, and they are moving parallel. There is a mutual capacitance and there is mutual inductance. What we are saying, so this is the scenario. And if for interconnect models, look, the technology node is moving towards smaller size. Resistance was initially ignored, then lumped, then distributed, and finally it's distributed. And capacitance models also consideration also is changing from area capacitance to area and 2D fringing, then 2/3 dimension fringing, then lateral coupling. And now when it's less than 25 micron, its lateral coupling is dominant. And inductance, first up to this it was ignored, and now it's become important. And circuit model, lumped C, lumped RC, distributed RC, and distributed RLC. These are the circuit symbols. So we are done with this slide, and let's move to the next slide. Loop and partial inductance. So loop inductance is defined as the induced magnetic field in the loop by the unit current in other loop. This is a loop, J loop. Current Ij is flowing. So this flow of current in this J loop is inducing a magnetic flux in this I loop where I current is flowing. So L, that is induced loop inductance from one loop to another. It's a loop. So magnetic flux is induced from one loop to another. This is the loop inductance, where psi Ij represents the magnetic flux in loop I due to current Ij in loop J. Now, problem with loop inductance. Calculation of loop inductance require knowledge of return paths. When we are considering loop inductance, we need to know the return path because it's a loop. As long as we do not know the return path, the loop is not closed. Calculation of loop inductance is incomplete. It's really difficult to determine return path for on-chip interconnects explicitly since there is no ground plane. So it's calculating this one is return path calculation is tough. Almost everywhere coupled to many wires, and there are multiple return paths. Because it's a complex 3D geometry on the level of interconnect. So many interconnects running parallel, up, down, both sides. So it's a complex 3D geometry of interconnects. So determining a single return path is difficult. Almost everywhere is coupled to many wires, and we will see that this inductance property is basically it's a long range effect. For capacitance, we can consider the nearby elements, but for inductance, the effect decreases very slowly with distance. So almost everywhere coupled with many wires. So there is a complex 3D geometry, and at that situation, confirming a return path is difficult. So what we do, we take partial inductance in consideration. What is that? It was proposed by A. Rueli, and the partial element equivalent circuit method, PEC method. This is based on partial inductance. Partial inductance is the portion of loop inductance for a segment when its current returns via infinity. So it calculates based on that the return path is infinity. It returns from infinity. It can be directly applicable to circuit simulator like SPICE. Because ultimately we need to use them in tools. All these mathematical calculations and everything, we don't, with this complex geometry and tight time to market, we cannot do all these complex calculation by hand. So tools have to do it. So this is the model. We will talk about it later. And now properties of partial inductance. Partial self and mutual inductance are based on geometry only. They may be solved by using 2D and 3D field solver. 2D and 3D field solver, basically they calculate that Maxwell's equation. They solve Maxwell equation. The return path of the current loop may be determined through SPICE simulations. The partial self and mutual inductance may be frequency and proximity dependent. These are the properties of partial inductance. So we are done with this slide, and let's move to the next slide. TL model, a recap. We have discussed about transmission line model in last episode. It's just a small recap because after that we will talk about termination of transmission line. Inductance also distributed over the wire like R and C, and the transmission line model is at high frequency and state of art devices. It's a almost most accurate approximation, and signal propagates as a wave. These are the equations, and for insulating material, leakage conductance G is 0. So wave equation, that finally we get this equation where R, C, L, everything is per unit length because it's distributed per unit length value. And for lossless transmission line, R equal to 0, that is resistance 0 with step input, propagates with a speed root over 1 by LC. So from there we get delay per unit length EP. This is the LC. It's just a small recap. We have discussed it in detail in last episode, and this is the wave form. This is the input waveform, and transmission line, this is lossless transmission line, and this is lossy transmission line. Just a time shift. If there is lossless transmission line, not any part of the input signal is lost, almost transmitted like as it is. Although for lossless, its shape is changed, some portion of the signal is lost. So we are done with this slide, and now we will move to the next slide. Dependence of impedance on frequency. In a circuit with multiple current paths, the distribution of the current flow is frequency dependent. When a circuit have multiple current paths, distribution of the current flow become frequency dependent. How? At low frequency, current path is determined by resistance of the path. At high frequency, current path is determined by the inductance of the path. Low frequency, where we have that Z equal to R plus J omega L. At low frequency, this part is very small. R is much greater than Z. So, in forward current is going when return path is dependent like this, that low R, low resistance path, most of the current return through low resistance path, and a small portion of it returns through high resistance path. Although what happens at high frequency is completely different. For high frequency, R is much less than J omega L. So, for return current, it's like most of the current return to a low inductive path, and smaller part of the current returns with low resistance and high inductive part. And these are the current distribution equation. At low frequency, the equation is governed by R2 because this portion is negligible, and at high frequency, the equation is governed by L value because this portion is considerable and this is negligible. So this effect is primary source of inductance variation with frequency in integrated circuits. So now let's move to the next slide. Impact of on-chip inductance. So any current passing through a conductor creates a magnetic field. This magnetic field then induces a parasitic current either on the same metal, that is self-inductance, or on another metal crossing the magnetic field, that is mutual inductance. And if we focus on the resistance and inductance, we can express interconnect impedances and just see impedance. Omega L part is increasing like that and R is increasing like that with frequency. And now skin effect. It's a high frequency phenomena. As frequency increases, the current tends to flow closer to the conductor surface or skin, between the outer surface and a level called skin depth. At low frequency, it's homogeneous. At high frequency, no more homogeneous. It flows between outer surface and a length called skin depth. So skin depth is defined as the depth where the current density is just 1 by E, that is about 37% of the value at the surface. So from surface, the current density is decreasing, and when at each depth it becomes 1 by E, that is 37% of value at this surface. This is called the skin depth. And just look at this graph. Skin depth is decreasing with frequency. That means more the frequency increasing, the skin depth is decreasing. So more and more current is concentrated towards the surface. Skin effect increases the resistance parasitics of a conductor at high frequency. They also lead to frequency dependent value for the effective inductance and resistance seen by the current. Such effects must be included in the parasitic extraction to achieve accurate results. So skin effect not only increasing the resistance parasitics of a conductor, also changing the effective inductance and resistance seen by the current. Here we are done with this slide, and let's move to the next slide. Impact of on-chip inductance. Now proximity effect. So when two or more conductors carrying AC are close to each other, then distribution of current in each conductor is affected due to varying magnetic field of each other. The varying magnetic field produced by AC induced eddy currents in the adjacent conductor. When the nearby, this is important, when the nearby conductors carrying current in the same direction, the current is concentrated at the farthest side of the conductor. When current, these are two conductors adjacent to each other, current is flowing in the same direction, so current concentrated towards the farthest. When the nearby conductors are carrying current in opposite direction to each other, the current is concentrated at the nearest part of conductors. This effect is called proximity effect. So opposite direction, current is, suppose it's flowing this direction, it's coming this direction. So These are the close, concentrated at the nearest. So this side, close to each other. Current is flowing in opposite direction. Current is concentrated here in the nearest part. And when it's in the current flowing in both the conductors in the same direction, the current is concentrated on the farthest side. This is proximity effect. The proximity effect also increases with increase in frequency. And effective resistance of the conductor is increased due to proximity effect. So we are done with this slide. Now we are moving to the next slide. Difficulties with inductance. First is it depends on frequency. Second, inductance of wire requires knowledge of return path with this complex geometry. The VSS or VDD closes loop for each piece of interconnection. The return path is decided by signal pattern and interconnect geometry for a large range. Often a return path is not easily identified, particularly at layout stage. It's not necessarily through the silicon substrate. And silicon substrate cannot be considered as ground plane as the resistivity of the doped substrate layer is very high compared to the metal, and the substrate is too far away from the high-speed buses or clock wire. If we take the cross section, so these are the top metal layers here, then at somewhere here it's the substrate. So basically from top level wires, substrate, this is quite far. This is one reason, and another is silicon substrate, although it's doped, lightly doped, still its resistivity is much higher compared to the metal. So it's not a very feasible solution. Mutual coupling between wires decreases very slowly. Magnetic fields die out at a far distance as compared to the electric fields. It's another problem because for capacitance, what we do that considering near neighbors which is enough for capacitance is not enough for inductance. We consider only near neighbors. Mutual inductive coupling between wires decreases very slowly. We have to consider that quite far wire also. Calculations become complex. Reason of concern for high frequency designs because it frequency dependent. Inductance is not scalable, and inductance results in many high frequency poles and zeros, making reduced order model approximation difficult. We always make a trade-off between accuracy and time. We have to make it as much accurate possible, and we have to complete it within time also. A very accurate, at the same time very complex methodology to solve it, to model it, is not always a very viable solution. And inductance in the equations or when we solve in the system equations, inductance results many high frequency poles and zeros. And while discussing about Elmore delay, we said that Elmore delay might not be a very good approximation, although it works really well because it's quite simplified and it gives us first order solutions. Presence of multiple poles and zeros make the situation tougher because reduced order model approximation become very tough. So inductance creates quite a difficult situation in modern ICs. Now let's move to the next slide. Minimizing on-chip inductance. Dedicated ground wires. Increase the mutual inductance by making the signal wire and its return path to be as close as possible. Decrease the self-inductance by increasing the width of return path or by adding one or more ground wire between signal wires. First, it gets a return path and it increases the mutual inductance and decrease the self-inductance. Next method is differential signaling. This method has high signal to noise ratio due to common mode noise rejection. However, requires double the number of signal paths as compared to single-ended transmission network. The transmitter at the near end of the network converts the single-ended signal into an opposite polarity differential signal, while the receiver at the far end of the transmission line converts the differential signal into a single-ended form. So first, this is the single-ended input. When the transmitter get it and transmit it transmit in the original one and change the polarity, transmit both. That's why we are talking about that it requires double number of signal paths. And at receiver, it again convert it and make it a single-ended input, although it has a benefit of high signal to noise ratio. Now let's move to the next slide. Splitting of wires. There are two ground. These are two ground path and this is signal wire. Splitting a wide wire into several n parallel wires of about 2 skin depths with each may reduce the total reactance by a factor of n. That's a method. Another method is continuous power or ground plane. When signal travels a long distance for a current return without planes nearby, that causes inductive coupling. So ground and VDD. continuous power or ground plane greatly reduces the coupling because it's provide a return path. This impedance control low loss line, these are the multi-layer interconnect, and this is substrate. These lines are closer to the interconnects. That is a viable solution. Now let's move to the next slide. Buffer insertion. With inserted buffers, inductive coupling decreases slightly faster than linear rate. Each segment becomes more RC line than RLC line because L per segment scales down at a rate faster than RLC. So we can insert buffers to reduce inductive coupling, and that reduce inductive coupling slightly faster than a linear rate. Now shielding. Another method, shielding techniques are widely used to reduce capacitive and inductive coupling. Isolates an aggressor or noisy line from sensitive neighboring lines. Increases the noise tolerance of a sensitive line. The voltage of the shield line typically doesn't switch. By inserting a shield line between signal lines, changes in the effective interconnect capacitance is significantly reduced, resulting in less delay uncertainty. Inductive coupling and self-inductance can also be reduced by inserting shield lines, since the shield line provides a nearby current return path. So here a signal line is on both sides shield line and between signal line, and here shield line is in between two signal line. So it actually reduces coupling, and obviously the delay is decreased. Let's move to the next slide. Now termination. We said that we will discuss about transmission line termination. At this high frequency, obviously the wires behave as transmission line, and the behavior of a transmission line is strongly influenced by termination of line. The termination determines how much of wave is reflected upon arrival at the wire end. It must be R. This is expressed by the reflection coefficient rho that determines the relationship between the voltages and currents of the incident and reflected waveforms. Rho equal to R minus Z0, R plus Z0, where R is termination resistance and Z0 is characteristic impedance. So if R equal to 0, if the transmission line is terminated with the characteristic impedance, rho becomes 0. That means no part of the incident wave is reflected back. That's a perfectly matched termination. And when R is much greater than characteristic impedance, rho becomes 1. So the circuit will behave like it's open circuit termination. The whole part of the wave is returned. So the total voltage waveform after reflection is twice the incident one. And if R is 0, that is short circuited. The total voltage waveform after reflection equals to 0. Rho becomes minus 1. The total voltage waveform after reflection becomes 0. These are three typical cases. Now let's move to the next slide. Significance of termination. To reduce the coupling noise at the inputs of victim receivers, different termination methods are used, like shunt RC, series R, shunt series R, and shunt C, series R termination and diode termination. There are different types of termination, and each of them have their own advantages depending on the usage. We select them. And termination is really important to prevent ringing effect when signal or data traveling long path. Ringing is generated on the transitions of digital signals when a portion of the signal is reflected back down to the line due to a mismatch between the line impedance and terminating impedance. We know when it's perfectly matched, no part will be reflected back. If there is a mismatch, then obviously a part is reflect back. And if the mismatch, kind of a similar mismatch, is at the driving end, will re-reflect a further portion. Like here, if this is the input driver, it has a characteristic impedance. Driver also has an impedance, and if it's not matched, then again a part of it will get reflected back. This kept on happening. This creates the ringing effect, and look, it gives a oscillation kind of structure to the waveform. That's not desired one. The amplitude of the ringing depends on the degree of mismatch at either end of the line, while the frequency depends on the electrical length of the line. So how much it's mismatched depends on that amplitude of the ringing. So we are done with the slide. Now let's move to the next slide. Now finally, modeling of interconnect at high frequencies. So these are some models we use. At high frequencies, circuit dimensions become comparable to signal wavelengths, and it's not always possible to identify discrete parasitic element. There are some models used to extract parasitics at high frequencies. Field solver, we already mentioned it. Actually, field solver solves Maxwell's equation, finite element method, moment method, boundary element method, finite difference time domain method, transmission line matrix, partial element equivalent circuit or PEEC method. These all are used. We already have mentioned about PEEC method. So these are standard methods used to solve this, and the EDA tools use different models inside them. So these are the basically models used to solve the equations and to get the parasitics at high frequencies. Today we will conclude here. Today we have discussed about on-chip inductance. So we will conclude here. Now let's take a look at the pointers we are going to discuss in today's episode. First, what is signal integrity in physical design? Second, common signal integrity issues in PD. Third, what is crosstalk? Next, classification, rise and fall glitch. Then classification over and undershoot glitch. Next, what impacts glitch? Range of safe and unsafe glitch, crosstalk delay basics, negative crosstalk delay, then positive crosstalk delay, effects of crosstalk delay, crosstalk and RT level estimation, and finally mitigation methods of crosstalk. So let's move to the first slide. What is signal integrity in physical design? In digital electronics, a stream of binary data is transmitted as signal and it represented as voltage or current waveform. All signals are subject to noise, distortion, and loss. In digital electronics, we use digital signals. That is, these signals has two states. One is 0 and one is 1. And in any practical system, signals goes through noise, distortion, and loss. Signal integrity is the measure of quality of a signal as it travels from one point to another point. So in signal integrity, what we discuss or what we measure is that in a practical and realistic world, when a signal travels in a system, how much its quality degrades within the system while it's traveling from one point to another point. So obviously, when we discuss signal integrity, we must consider the reasons which make quality of signal degrade. Now, signal integrity is crucial as it ensures whether the data transmission is accurate, reliable, and immune to unwanted effects such as noise, distortion, and reflections. Now, when we talk about digital electronics, actually not exactly a single voltage value is considered state 1 or single voltage value is considered as state 0. There is a band of voltage. If the voltage remain within this to this value, we will call it 0 state. And if it's above some certain value and below some certain value, that is another a band of values, we call it state 1. So when a signal in a realistic world goes through this noise, distortion, and reflections, so obviously its value gets changed. We must ensure how reliable the data is transmitted. Suppose due to impact of noise or distortion, value gets decreased. If a state 1 is getting transmitted and then value degradation happens and it become below certain level, so after that it will not get considered as state 1, it will become state 0. So it's very important to understand, to analyze signal integrity issues to ensure quality of transmitted data. Now, if the signal faces above mentioned unwanted effect continuously, it can lead to erroneous data transmission. That which I have just mentioned about that. That continuously, if a signal gets distorted, doesn't remain in the same state as we are transmitting. So it's a diagram from driver, signal is sent and receiver will catch it. By that time, this distortion, noise, distortion and reflection, these can happen. These three effects, noise, distortion and reflection, this thing can affect in this part. And when it goes to this receiver, so maybe it might not reach in the voltage level it's desired here. So these are the points we have covered. This point, what is signal integrity and why signal integrity is crucial, and what will happen if some degradation happens. So this is the ideal voltage form, and in real world it doesn't like that. Neither it's so straight here. The signal integrity mainly deals with timing and quality of the signal. Whatever circuit and modules we design, timing closure is there because we deal with sequential components in the circuit. So their performance is time dependent, depends on clock. The signal get delayed, that timing violation occurs, and quality of the signal, magnitude of the voltage that can differ from what is expected. Signal integrity is both an interconnect level problem as well as system level problem. Interconnect, obviously signal integrity interconnect level problem because there are so many issues comes from interconnect level like crosstalk, ohmic voltage drop. These all comes from interconnect level. At the same time, it's system level problem also. Any design have some signal integrity problem and they generally do not interfere with the functionality of the system by creating excessive until the system deals with high frequency signals. So as we move to high frequency operation, the problem become more severe. No system is ideal. So signal integrity issues are there, but in a manageable amount. Distortions and noise are there. That's why we define noise margin. Actually, this noise margin calculation is within the design thing. So people always design keeping in mind about noise margin and all. If it remains within the noise margin, it will function that way because it's not an ideal system. It's a real world system. But whenever we are at high frequency signals, we are dealing with them. That problem really interfere with the performance of the system. High frequency state of art ICs are, for them, signal integrity issues are more severe. So let's move to the next slide. Common signal integrity issues in PD. In a digital system, signal integrity analysis are done at 3 levels. First, logic level, second, circuit level, third, EM field level, that is electromagnetic field level. In logic level analysis, so 3 level we do the analysis. Logic level, circuit level, and electromagnetic field level. In logic level analysis, signal integrity issues can be easily identified. Circuit level signal integrity analysis is based on interconnect modeling. Interconnect modeling we have discussed in one of our previous episode. Interconnect modeling, and there we calculated delay due to interconnects and all. Here we try to model a piece of interconnect including resistive, capacitive and inductive effect. That is parasitic effect and impact of parasitics, how the interconnects behave and all. And at electromagnetic level, most of the signal integrity issues are reflection, crosstalk, ground bounce, etc. Reflection, we have talked about termination of transmission line and reflection. Crosstalk also we have discussed in the first episode of this series a little bit. Today we will elaborate those points. And ground bounce, we have a separate episode on that. Link is provided in the description. Both link of the video and link of the article in TechSimplifiedTV.in. So you can watch the video, you can read the article. This reflection issue, crosstalk issue and ground bounce, these are electromagnetic level issues. Now circuit level analysis obtain a good signal integrity solution at low frequency, whereas for state-of-art ICs with small dimension and high operating frequency, EM level analysis is more accurate to describe the effect. Since we have moved to more smaller dimension devices, so in state-of-art ICs which are operating at high frequency, for them analysis is basically a little bit tougher compared to the previous generation ICs. Now SPICE tools are used to check signal integrity in nodal analysis and they solve voltage and current in RLC circuit. So SPICE tools are used to check signal integrity in nodal analysis, circuit nodal analysis they do to check signal integrity issues and they solve equations in RLC circuit. So these are the major issues concerning signal integrity. One is crosstalk delay, crosstalk noise. Today we will discuss about these two. And ringing and ground bounce. Ringing we discussed in last episode. Ground bounce, the link of both the video and article is provided in the description. Now IR or voltage drop in power line, we mentioned about it in very first episode. And electromigration, we have separate 3 episodes, link of video mentioned in the description. And finally, manufacturing related issues that if not addressed can lead to chip failure, that is antenna effect. Antenna effect, on antenna effect also we have a video and article, links are provided in the description box. So today we will talk about these two. So there are 6 effects. Now let's move to the next slide. So what is crosstalk? Crosstalk is undesirable electrical interaction between two or more adjacent nets due to capacitive coupling. Switching of signal in one net, which is called aggressor net, can interfere neighboring net, that is called victim net, due to coupling capacitance. This is called crosstalk. This one is aggressor net and this is victim net. Switching happening in this net. Switching happening in this net, and that switching due to this coupling between these two nets, the coupling between these two nets, logic state of this net is changed due to this net. So this is aggressor net and this is victim net. Aggressor is a net which creates impact on the other net. Victim is a net which impacted by aggressor. And crosstalk has two effects, crosstalk noise and crosstalk delay. Crosstalk noise or crosstalk glitch. Signal transition in aggressor causes a noise bump or glitch on victim net. This is known as crosstalk noise. Crosstalk noise or glitch or bump occurs when aggressor net switches and the victim nets remain in a steady state. So crosstalk noise or glitch occurs in victim net when victim net remain at steady state, steady 0 or steady 1, and aggressor net is switching from 0 to 1 or 1 to 0. Another is crosstalk delay or crosstalk delta delay. Signal transition in aggressor create delay in output transition of victim. This is known as crosstalk delay. Crosstalk delay occurs when both aggressor and victim net switch together. So we are done with this slide. Now let's move to the next slide. Now, classification, rise and fall glitch. We have discussed about crosstalk noise or glitch. Now let's see which kind of glitch happens when. Now rise glitch. This is the diagram. This is gate 1, gate 2. This is the aggressor net as mentioned. This is gate 3, gate 4. This is the victim net as mentioned here. Now this is the coupling capacitance between these two nodes, and this is aggressor node basically, and this is victim node. And C1, these are capacitances by which this net is grounded. Victim net is at a steady low. Now this is the condition. Victim net is at the steady low. Its logic state is not changing. Aggressor net is switching low to high, high to low, so low to high. So output here it is low to high. So gate 1 input is 1 to 0, and obviously gate 1 output will change because we can see it's a NOT gate. So 0 to 1, obviously A, it's connected with a resistor, so it's at node A, the state will change from 0 to 1. And since this node V is at constant 0, and there is a mutual coupling capacitance between these two nodes, so node A will try to change the state of victim net, that is node V. So node A at changing at 0 to 1, CM starts to get, that is mutual capacitance starts to get charged. Output of gate 3 and node V at 0. Leakage current through that's coupling capacitance create a rise in voltage glitch at V. So though it's at this point it's 0, so if we measure voltage across this resistor, although it should be at 0 state, there a glitch or spike or bump occurs. That is the rise glitch. Now comes fall glitch. At fall glitch, victim net is at steady high. Steady high at, we can see, and this aggressor net is switching high to low. So input it's low to high. So obviously here it will be high to low. So point A is high to low, node A. And at node V it's constant 1. Again, output of gate 3 and node V at 1. Node A switches from 0 to 1 and node V at 1. Leakage current flow through CM from V to A. Previous case it was flowing from here to here. Now it's flowing from here to here and create fall in potential at V. Leakage current is flowing from this direction V to A. So although it should remain at constant or steady high one state, voltage falls. That is fall glitch. So we are done with the slide. Let's move to the next slide. Classification, over and undershoot glitch. Well, overshoot glitch, victim net is at steady high and aggressor net is switching from low to high. So when aggressor node is switching from low to high and victim is at 0, that is rise glitch. If victim is at steady 0, that is here at steady 0, and aggressor is pulling it up, so there will be a glitch, but that is not crossing the maximum allowable value, right? And when the aggression node is high to low, moving high to low, and the victim is at steady 1, that is fall glitch. This one, it was at high and then going down, pulling it down. So aggression net is pulling it down. So although it's within the range, what happens in overshoot glitch? Overshoot glitch is the aggressor is moving from low to high, although the victim is at steady 1. So it is already at steady 1, and if the aggression net pull the voltage state of victim, then from 1, if it's move upward, so it is crossing the maximum limit. That is overshoot glitch. Overshooting. And opposite happens while it's in case of undershoot glitch. Victim net voltage is at steady low. It's already in low, and aggression net is switching from high to low. So when it's moving from 1 to 0, it will pull down the victim net, inducing undershoot glitch by taking the victim net voltage below its steady low. It's even moving from below steady low, below the allowable low. So that is undershoot glitch. So we are done with the slide. Let's move to the next slide. What impacts glitch? Not all glitches are considered unsafe for circuit operation. Safe, unsafe decided by glitch height. Now, glitch magnitude or height of the glitch is determined by few factors, such as value of coupling capacitance. Magnitude of glitch would be higher if the coupling capacitance value is higher. Slew of the aggression net. If the output drives, slew means how fast this signal, ideally we take like this, but actually it doesn't happen. It takes, there is no instantaneous thing, so it will be something like this and that. This how fast, this rate of change, that is called slew. So if that is very sharp, then the driver of the aggression net is really strong. It has high driving strength. So slew of a aggressor net defines how strong the driver of that net is. If output drive strength of cell that is driving the aggression net is high, slew of aggression net is faster. The faster slew of aggression net results in high magnitude of glitch. That means the aggression net is more powerful compared to the victim net. More powerful aggression net is, it will impact more, the glitch will be higher. So drive strength of aggressor and victim net. If driving strength of aggressor net is high, the magnitude of glitch will be higher, whereas if driving strength of victim net is higher, it's not easy to influence it. It's a comparative one. If victim net grounded capacitances are small, then magnitude of glitch will be large. So these are basically 4 factors which impact the magnitude of the glitch introduced in victim net by aggression net. Now, what will happen if multiple aggressors are present? So when multiple aggressors are present and they switch concurrently, the impact on victim net is get added. Suppose there are multiple aggressors, multiple aggression nodes are there. They are impacting one victim net. Now, concurrent switching is an ideal case. All the nets are switching at the same time. That's a ideal case. In reality, what happens, suppose there are 4 aggression net, 2 switches, one is switching, and then after few nanoseconds, some other net is switching. So for that time period, any 2 or any 3 or multiple, depending on the number of aggression net, they are active. Suppose if that is the time, suppose for one aggression node is steady 1, then after some time another one, when before it's completely switched, go to 0 state, another net is getting switched on. So switching happens. So in analysis of such situation, what happens? So the impact on victim net depends on the contribution of each aggression node on that victim net for a time window. That time we will consider analysis depending on time window. For which time window, how many nets are active on that victim net or switching. So depending on that, get added. In this case, we do the analysis based on time window. So we are done with this slide. Let's move to the next slide. Range of safe and unsafe glitch. We said that not all glitches are unsafe. Some are safe also, depends on magnitude. So safe glitch has no effect on logic state or victim net. Glitch is there, but it's not impacting. So we'll not get bothered by it. If glitch height is less than noise margin low, NML a safe glitch. So this is the noise margin low, this is the range of NML, and this is the range of NMH. Any glitch below this maximum, this is the range of NML, that is noise margin low, we call it safe. And here we can see that noise margin high level, it has within that range, it's obviously unsafe, and this is potentially unsafe. Glitch height is greater than noise margin high, unsafe glitch, and if NML is less than glitch height, less than NMH, an unpredictable case, this one potentially unsafe. Noise margin is a parameter that determines the allowable noise voltage on input without affecting output. How much noise could be there in input so that it doesn't affect the output? It's there, but it's not impacting. That's the noise margin. So noise margin, or basically immunity, expressed in terms of noise margin low and noise margin high. What is noise margin low? That is VIL minus VOL, that is difference in magnitude between the maximum low output voltage of driving gate and the maximum input low voltage recognized by the driven gate. This is the driving gate and this is driving this driven gate. So difference in magnitude between the maximum low output of this driving gate and the maximum input low voltage recognized by the driven gate. This is the calculation. And NMH is difference in magnitude between the minimum high output voltage of the driving gate and the minimum input high voltage recognized by the receiving gate. This is the calculation. So we will go by this one, that the noise level must be within this safe zone. So we are sorted. As long as noise or the glitch above this line, we are not really sorted. There are reason to get worried. And now let's move to the next slide. Now crosstalk delay basic. Till now we have talked about crosstalk noise, now crosstalk delay. Crosstalk delay occurs when both aggressor and victim net switching. So in case of crosstalk noise, victim net was always at steady state. It was not switching. When both aggressor net and victim net, they both are switching, what will happen? So that effect is crosstalk delay, and that analysis is crosstalk delay analysis. Crosstalk delay occurs when both aggressor and victim net switching, and these may lead up to setup and hold timing violation. It increase or decrease the delay of a cell depending upon the switching direction of aggressor and victim nets. In case of crosstalk delay, we will discuss about that aggressor net, which direction is going, that is from 0 to 1 or 1 to 0, and victim net 0 to 1 or 1 to 0. Like same, they are switching in same direction, low to high or high to low, or opposite, like one is switching from 0 to 1 and another is from 1 to 0, that is high to low. So we are done with this slide. Let's move to the next slide. Now negative crosstalk delay. The small mistake, this waveform would be like this. It is written properly, but it's not. So negative crosstalk, aggressor and victim net switch in the same direction. Both net switches from low to high. So here also it's 0 to 1. Here also it's 0 to 1. There is a small mistake. I have corrected this one. If aggressor has higher driving strength, transition will happen faster. If this aggressor net is strong compared to victim net, then its transition will happen faster. We are assuming that if aggressor net has more driving strength, then this point will be at higher potential compared to V. So node A will try to pull up the victim node. Transition of victim node will have a bump. So it's moving. Otherwise, without any interruption from aggressor node, its transition should have like this. Now, point A or node A is pulling the voltage or the logic state of this node V, so it will pull it. So here the voltage get pulled up, and with its natural slew, it would have been, transition happen would have been at this zone. This transition just happens before. So there is a delta shift. So actually victim net will reach from 0 to 1 earlier and transition time will decrease. And crosstalk will decrease the delay by delta, and the new delay will be d minus delta. So usually it would happen like this. It would have this transition time would have taken. Because of action of this aggressor net, this transition is happening earlier by a small time window delta. Here crosstalk is actually decreasing the transition time of victim net. So it's called negative crosstalk because it's reducing the time. Now we will move to positive crosstalk delay. Here aggressor and victim net switch in the opposite direction. Here it's 0 to 1 and this is moving from 1 to 0. Yeah, here also a small mistake. Sorry, I have not noticed it earlier. So here aggression net and node A switches from 0 to 1, and node A will try to pull up node V. V switches from 1 to 0. It was 1 and now it's moving to 0. So transition of victim node will have a bump. It's without any interruption. It would have been like this. And since it's trying to pull it, there will be a bump. If there is no interruption, it would have transitioned here. It will reach 0. And since it's pulling up, this victim net will reach 0 a little bit later. That is delta. That is this delta time is added with the delay. This is called D plus delta. So it's actually increasing, positive. It's increasing the delay. We are done with this slide. Now let's move to the next slide. That is effects of crosstalk delay. Effect on clock tree. Crosstalk can unbalance a balanced clock tree. Crosstalk delay can change the latency of balanced path and the clock tree become unbalanced. Suppose different branch of clock tree are balanced, they will reach and perfectly time, and some in one path and between one path delay is introduced. So obviously its total timing, it will not match with the other path. So our balanced clock tree become imbalanced. Now effect on setup timing. Effect on setup timing. For setup timing, data should reach the capture flop before the required time of capture flop. There are two flip-flop. One is launch flip-flop. One is capture flip-flop. That is launching clock path. That is capture clock path. And this is the common path. So suppose here, there are some cells and drivers are here. We have shown that with 1, 2, 3, 4 and 5, 6. If delay is include here and it's a positive delay, so it will reach later. If so, for a setup timing, the condition is that the data should reach at the capture flop before the required time of capture flop. That flip-flop should not wait. Data must flow from here to here. So data is ready. When clock reached, the state will change and it will reflect here. So if delta delay is positive delta delay introduced here, it will reach later. So there will setup violation can occur. Another one is if delay of this clock path reduced. So it will be ready. This clock is ready, although data has not come here. It will come its natural time and it's reduced. So it will be there, and our prerequisite is that data should be present at here before the clock comes. So there are two things. One, increase of delay in data path or launch clock path, and decrease in delay on capture clock path. In these two cases, setup timing violation can happen. And now effect on hold timing. For hold timing, data must be stable for minimum amount of time after the clock's active age. So for hold timing, data must stay there. So if decrease of delay in data path and launch clock, if this clock reduced, this data path reduced, and increase of delay in capture clock, and this clock comes later, then hold violation can happen, because for hold timing, the data must be stable after clock's active age. Otherwise, the flip-flop give ambiguous data. So this delay is reduced. It's already reached there, and this data path, this clock is getting delayed. It's getting positive delay and it's getting negative delay. So it will cause the decrease of delay in data path and launch clock, and increase of delay in the capture clock will create the hold violation. So this way, crosstalk delay can impact setup timing and hold timing. We are done with this slide. Now let's move to the next slide. Crosstalk and RT level estimation. This is basically high level synthesis, logic synthesis and physical level synthesis. These are three level of abstraction used in this VLSI design methodology. So here we will talk crosstalk and RT, that is register transistor level estimation. How we can do estimation at register transistor level, and why should we think to do it? Because we are doing at physical design. So each design stage has its own model for crosstalk. Trade-offs exist between accuracy and complexity of this different model. So more accurate, it's more complex and time consuming also. The cost involved in detecting errors and correcting them increases by a factor of 10 between each abstraction level as we move top down in ASIC design flow. So as we move every step, so the cost involved in correcting and detecting errors increases by 10 times. So if we can detect any error or correction method or correct anything to correct at higher abstraction level, then it's less expensive. Detecting crosstalk sensitivity at gate level 0 is 10 times more expensive than detecting at RT level. Some level parameters have direct impact on crosstalk noise problem, and those cannot be accurately determined at higher abstraction level. Such parameters are The position of models relative to one another can be determined after floor planning. So we cannot assume it at behavioral level. Then only from floor planning we can assume that. So another is the route of each wire that can be determined after floor planning only. We can only determine it. At behavioral model we cannot do it. The aggressor of a given wire in both the horizontal and vertical planes can be determined after floor planning. So we cannot do at higher level of abstraction. Thus, high level crosstalk estimation includes mathematical and statistical process. And if we can do a little bit of our analysis at behavioral level, then it will be cost effective. It will be easier for us. There are so many research papers and research theses are there, and it's mostly based on statistical and mathematical methods. We will not talk about it detail because our concentration is only on crosstalk in PD. So we are just trying to give you an idea that with even existing models and methods, some researchers are always there to find a new way, making it more cost effective, more time effective. So we just to give an idea about that, we have introduced this slide. So we are done with this slide. Now let's move to the next slide. So mitigation methods of crosstalk: increasing the space between aggressor and victim net. If the distance between aggressor and victim nets is increased, the mutual inductance or mutual capacitance between them will decrease. Insertion of shielding net. Inserting a net which is connected to VSS VDD between critical aggressor and victim net is a method. This new net between works as shield, and this process is known as shielding. Process of shielding stops direct coupling between aggressor and victim net, and since the shielding net remain at constant potential, chances of crosstalk is completely waived off. Upgrading drive strength of victim cell. If we upgrade the driving strength of victim cell, it will not be easy to change its logic state. Downgrading the driving strength of aggressor cell. If we downgrade the driving strength of aggressor cell, its impact on victim cell will decrease. Buffer insertion. Insertion of buffer effectively boosts the victim net strength. Guard ring in the substrate used to shield the analog circuitry from digital noise. So we are done with this slide. That's all we had for our today's episode, that is signal integrity and crosstalk in physical design. We will conclude our episode here today. Now let's take a look at the pointers we are going to discuss in today's episode. First, VLSI milestone and multi-level metallization. Next, metallization. Here we will talk about what is metallization, why it's needed, different types of metallization, etc. Next, multi-level metallization. We all know with time, device dimension has reduced, and at the same time, metal layers has increased to make electrical connection for more complex circuits. So in this slide, we will talk about multi-level metallization. Next, components of multi-level metallization. After that, interconnect material. Here we will talk about aluminum. Next, reliability of aluminum. After that, interconnect material. And here we will talk about copper. Then, single and dual Damascene process. Single and dual Damascene are two processes by which copper interconnects are developed. That's quite different from fabrication of aluminum interconnect. Next, aluminum interconnect versus copper interconnect. After that, we will talk about low-K intermetal dielectric, physics of low-K dielectric, and finally, different low-K material. We are done with this slide, so we will move to the next slide. VLSI milestone and multi-level metallization. This diagram, we are taking reference for last few episodes on milestones. Here we can see at 180 nanometer, copper interconnect, 6 metal layer. Then 130 nanometer node, it's low-K dielectric, 8 metal layer. After that 45 nanometer, 10 metal layer, 12 metal layer. Feature size is reducing, number of metal layers are increasing. Moore's law has been driving and guiding force for last few decades. With progressing node, circuit complexity has increased. Feature size reduced, individual device size reduced. As a result, more and more devices could be accommodated within the chip. Now, reduced dimension has made short channel effect, parasitic effect more severe. We have already discussed about parasitic effect in our interconnect series. Keep up with pace of scaling, new material, new device structure was found and introduced. We know that high K material has been introduced instead of silicon dioxide. In this whole journey from 180 nanometer to 10 nanometer, in this journey, new device structure like SOI, FinFET, we have already discussed in 2 different episodes, that has been introduced. New material like strained silicon, that is introduced. And now another 2 different material, that is low K and copper interconnect, that is interconnect metal. Initially it was aluminum, that has been replaced by copper, and a low K dielectric, that is introduced as a interlayer dielectric or intermetal layer dielectric. So that is also changed. Higher package densities and design flexibility was achieved by increasing interconnect layer. With reducing feature size, interconnect layer increased because as the individual device size reduced, so within the same chip area, now more and more devices could be placed. So package density increased, and to make flexible connectivity, copper has been introduced. To increase circuit performance, different materials incorporated at different part of total interconnect network. At the wafer, there are devices, and then above it, these interconnects are used like that and interconnected with each other through via. So these all are part of interconnect network, and at different points, different materials are also used. So research led to new intermetal dielectric layer. So multi-level metallization, copper interconnect, and low K dielectric, these 3 points are very closely knitted. The introduction of low K materials in CMOS technology is a good example of how industrial needs drive new fundamental and applied research topics in science. So we are done with this slide. We will move to the next slide. Now multi-level metallization. First we will talk about multi-level metallization. Conductive films provide electrical interconnection among devices as well as the outside. 3 categories of interconnection: gate, contact, and interconnect. If that is the substrate, here are the devices. Interconnect network is above on that. Devices are connected to the interconnect, this network, that is called active contact. And 2 metal layers are connected, that is via. Among devices, there are 3 types of. One is contact. This is basically contact. One is gate and interconnect. Polysilicon and silicide are frequently used for gate connection. We have already covered in polysilicon episode of VLSI milestone series about polysilicon. Silicide are frequently used for gate connection. Aluminium or copper are used as contact and second level interconnection to the outside. In some cases, a multiple layer structure involving a diffusion barrier is used. Titanium, platinum, gold, or titanium, palladium, gold is useful in providing relatable connection to external components. We will see in much detail what is diffusion barrier later. Circuit speed is controlled by resistance and capacitance of the interconnect. Metallization is deposited by either physical vapor deposition or chemical vapor deposition. These 2 are the process by which this metallization is deposited or created. Now, circuit speed is controlled by resistance and capacitance of the interconnect. By circuit speed and resistance and capacitance is not only parameter of the dimension but also an intrinsic parameter of the material. So there are 2 factors which we can control. When we try to control circuit speed by controlling interconnect parameters, either we can change the material altogether, the resistance and capacitance value will get changed. These are intrinsic to a material. Another point is we can change their dimensions. So cross section can be changed, length can be changed. So by that designing we can do so that we can change the circuit speed. Next, what are the desired properties of metallization for ICs? First, low resistivity, easy to form and easy to etch for pattern generation. Sorry, there is a spelling mistake. There should be generation. Already process steps are established, and now if we include a material which is tough to form and tough to etch, then the whole process will get hampered. Resistivity must be low, resistance will be low, so high current will flow. Easy to form and easy to etch. Otherwise, pattern cannot be generated easily. Should be stable in oxidizing ambient and oxidizable. Mechanical stability, good adherence and low stress. Surface smoothness. Surface smoothness is also required. Mechanical stability is important because it's not that only one layer is deposited, then again the same cycles are repeated. Multiple cycles are repeated. We have discussed this in the first episode of Interconnect series also. You can watch that. First, this metal layer is formed. Then next, this metal layer is formed. While this metal 2 layer is forming, if we select such a material that cannot handle this high temperature, that will not done. This metal must be deposited, and even after multiple thermal cycles, it will remain same. Should be stable in oxidizing ambience, oxidizable, mechanical stability, good adherence and low stress. All these properties are required. Must be stable throughout process including high temperatures, sinter, dry wet oxidation, decoding, passivation and metallization. All tough processes and it must survive. No reaction with final metals. Should not contaminate devices, wafers or working apparatus. Good device characteristics and lifetimes. For window contacts, low contact resistance, minimal junction penetration and low electromigration. Electromigration, we all know multiple times in multiple episodes. I have talked about, even in today's episode, in some slide I will talk again about electromigration. Electromigration is highly dependent on temperature also. So at high temperature, high speed operation, if the material is not reliable, then it's not a good candidate for IC designing. So that's the basic about metallization. We are done with this slide. We will move to the next slide. Multi-level metallization. We know multi-level metallization is used. Do you know why it's used and what are other related issues are there with multi-level metallization? Now we will understand that. RC time delay. We know it's basically a figure of merit to understand how good our interconnect is working. So as technology processes, LS decreases, RC delay increases. It's a metal and it has some parasitic resistance and capacitance. R, that is expression of R, that is resistance, rho L by height and width. If L is longer, then resistance will be higher. C, that has dependency on L. This is the expression of RC. What is RC time delay? We have already discussed in interconnect series in details. RC delay should not be very high, otherwise circuit cannot perform well. So length of wear must be kept small. Our requirement is that RC must be less. Higher resistivity, higher capacitance is not required. If we multiply R and C, their product is even bigger. So R and C individually should kept lower. To keep it low, L must be kept low. L means length. The length of wear must be kept small. How is it possible? Many things we have to connect. If we do not break it in multiple layers, otherwise it will cross there and go here, like there. It will be longer if we not break that length and make it multi-level. So multi-level necessary of multi-level metallization arises from there to keep RC less. Now lower resistivity metal for interconnect wearing is also required. How can we reduce R? Rho can be reduced, L can be reduced. Reducing L will result in multi-level metallization. Another point to reduce R is rho, that is resistivity. Resistivity is an intrinsic property of the material. So lower resistivity metal for interconnect wiring. So industry moved from aluminum to copper interconnect. Next, lower dielectric constant. Lower dielectric constant material for interlayer dielectric, that is low K material. So these are basically 3 points which led to multi-level metallization, copper interconnect and low K intermetal dielectric. This is a representation. Suppose we are taking a small cross section. 2 metal layers are going and in between dielectric. So metal layers, it has resistivity, these two are conductive, in between dielectric layer. So it will form a parallel plate capacitor. If epsilon of this material is higher, so effective capacitance will be higher. And more capacitance means circuit turn on time will be higher. First this internal parasitic capacitance will get charged, then only the circuit will turn on. There will be delay. So time delay that will increase. While we are considering multi-level metallization, copper interconnect and low K, there are few more points which we must take care. Contact resistance. Low contact resistance to semiconductor device. Connection to semiconductor, that should be contact resistance must be less. It should be ideally ohmic contact. When for N-type, for P-type material, for lightly doped and heavily doped N-type material, these responses, IV response is completely different. We need a low contact resistance. Now immunity to EM. Reliable long-term operation. We have an episode on reliability and IC failure in CMOS. Watch the video. There I have discussed this electromigration in detail there also. So reliability and EM is a reliability issue and immunity to EM is very important. Otherwise the circuit will fail. Multi-level metallization. So state-of-art ICs have millions of transistors and connecting them all to some voltage and current supply without wires crossing is a real challenge. This is the device level. Every device has a voltage supply should be connected to it. Then it's connected to some other device also. So this connection is very critical. And without so many devices, so many wires, without crossing each other, designing this connectivity is a real challenge. Now, 3D network of interconnections is called multi-level metallization. Multi-level metallization increases interconnect capacity and reduces resistance and capacity. Now, metal interconnections. Metal interconnection stretches over several planes and isolated by insulating dielectric layer. This is basically interconnect dielectric. Multiple layers of metal isolated by insulating dielectric layers. Interconnected by wiring through holes in the dielectric plane. So these dielectric planes are there and above on these metal layers are there, below these layers, and in between that these holes are like this and they are connected. These are vias. So they pass through this dielectric layer plane. Benefit of multi-level metallization. Reduce interconnection length and reduce RC, higher package density and design flexibility. Design flexibility also required, otherwise huge number of devices and their interconnects is a very complex affair. We are done with this slide. Now we will move to the next slide. Now components of multi-level metallization. So components of multi-level metallization circuit are interconnects, contacts, vias, intermetal dielectric and passivation. Now let's see what are these things. Active devices are electrically connected to each other, obviously. These devices, active devices means MOSFETs or transistors. So these devices are electrically connected to each other. They are connected to the outside world through their input and output on bonding pads. They will get stimuli from outside and results are also measured at outside. So there should be contact with outside world. So that is done through bonding pads. Now contact is connections to source, drain or poly. Active device MOSFET, there are 3 connections with it, source, drain and poly. So contact is connection with them. Vias are connections between interconnect levels. Interconnects are separated from each other by dielectric layer. Now vias connection interconnects through these layers. These ILDs or interlayer dielectric. They connect through these layers. These components are part of metallization or backend or BEOL. Backend of line. Now local interconnects are first lowest level of interconnects. They are small and short and connect gates, sources and drains. Polysilicon, silicide, titanium nitride, tungsten can act as local interconnect. Now local interconnects, this one, local interconnects are short in length. First or lowest level of interconnect. This is the first level. These are active contacts and here this is the first level of interconnect. Now, local interconnects can afford to have higher resistivity since they do not travel long distances. So, if we can use some material which has higher resistivities because they are not running really long, they must be able to withstand higher processing temperatures because this is fabricated first, then multiple, all the layers are fabricated after that. Now, global interconnects are usually made of aluminum or copper. They are above the local interconnect level. Global interconnects are thick, long and widely spaced. They travel longer distances between different devices and different parts of circuit and therefore are always metal with lower resistance. They are thick, long and widely spaced. They'll travel longer distances, so they must be with lower resistivities. After completion of metallization, passivation layer is formed to protect internal semiconductor devices. Passivation layers are typically formed with deposition of oxide layer and a nitride layer. These are the components of multi-level metallization. We are done with this slide. We will move to the next slide. Now we will talk about copper as an interconnect material. Although we will start discussing with aluminum. We will first talk about aluminum, its advantages and disadvantages, which we can overcome with copper. Interconnect material, aluminum. Aluminum interconnects were used as standard for a long time in chip making. In the late 1990s, chip makers switched to copper. Now, advantages. What are the advantages? It's a good conductor. It can form mechanical bonds with silicon. It can form low resistance ohmic contacts with heavily doped N-type and P-type silicon. Corrosion resistant. There are some disadvantages also. Low melting point, junction spiking, electromigration and stress migration. Low melting point, we have already talked about low melting point in some other episode also, where we have discussed about self-aligned gate processes in polysilicon. You can refer to polysilicon as a gate material third episode on this series. Go and watch. That's low melting point has led to another thing also, that is self-aligned gate formation and polysilicon. Now, junction spiking. Use of pure aluminum leads to diffusion of silicon into the metal. These are the junction aluminum spikes. Silicon reacts with metallization at only 200 to 250 degrees centigrade. This diffusion of silicon causes cavities at the interface of both materials, which are then filled by aluminum. So at 200 and 250 degrees centigrade, silicon reacts with metallization and it diffuses. Silicon causes cavities. This cavity is then filled by aluminum. This leads to spikes which can cause short circuit if they reach through the doped region into silicon crystal beneath. It's creating a short circuit. Size of this spike depends on temperature at which aluminum was deposited. To avoid spikes, a deep ion implantation can be introduced at the location of the vias. To avoid these spikes, a deep ion implantation can be introduced at the location. Thus, this junction short is happening. Thus, the spike do not reach into the substrate. Now, another point is an alloy of aluminum and silicon can be used. Silicon 1 to 2%. Since aluminum now already contains silicon, there will be no diffusion out of the substrate. It happens at 200 to 250 degrees centigrade temperature. Silicon diffuses, and while it diffuses, it leaves a space that creates a void, a cavity. That cavity is getting filled by aluminum. Now, alloy of aluminum and silicon if we use, then what happens? So, already silicon or aluminum present there. So, the existing silicon doesn't move, doesn't leave place. So, spiking will not happen. A barrier of different materials such as titanium, titan nitride or tungsten is deposited as barrier layer. This is barrier material is done. Look here, barrier material is there. So, there is no spiking. That is the junction spike. We are done with this slide. We will move to the next slide. Reliability of aluminum. First, we will discuss about electromigration. We know electromigration is the movement of atoms in metal film due to momentum transfer from the electron carrying current. Under high current density condition, metal atom movement creates void in some region and metal pile up or hillock in the other region. Here void is created. If this void increases, it becomes open circuit. And here hillock is created. If this grows a little bit more, it will touch the another interconnect and short circuit will happen. What is the solution? Alloying with copper. 0.5% copper. Inclusion of copper can reduce that. Another point is stress migration. So, in case of stress migration, hillock happens, void happens. Due to difference between coefficient of thermal expansion of aluminum and silicon, it's a system. Silicon, then silicon dioxide, aluminum. Even after first layer of deposition of aluminum, many more layers will be there formed and many more layers deposition and their processing steps means more thermal cycles. So, while it's already is present there, more thermal cycles are happening. Thermal expansion coefficients of two different materials are obviously different. In presence of high temperature, they doesn't expand equally. And when this heat is removed, it doesn't contract similarly. And even if it contracts, it never comes to its original form. We have discussed this stress migration in reliability and IC failure episode in detail. It will never come back to its original position. So always there will be some strain. Strain will be there in the structure. High compressive stresses appear in aluminum at high temperatures. Now movement of aluminum occurs along grain boundary. These metal grains, these boundary, this movement happen. Now whole grain of aluminum pushed upward forming hillocks. This hillock is formed. Now tensile stress creates void, crack, that is electrically open, and compressive stress creates hillocks, that is electrical short. Now, as a result, this void and hillock, this surface doesn't remain same. The surface becoming rough. So, rough surface topography making lithography and etch difficult. So, we are done with this slide. We will move to the next slide and try to understand why industry has moved to copper over aluminum. Interconnect material, copper. So, what are the benefits of copper? Higher conductivity, more electromigration resistance, higher tensile strength, higher thermal conductivity, higher melting point, low coefficient of thermal expansion, high specific heat, lesser joule heat. Self-heating also is another issue. In case of reliability, you can refer to the reliability issues episode. Self-heating can lead to IC failure. What are the drawback of copper? Lack of feasible dry etching method. That will actually lead to different processing step. Lack of self-passivating oxide similar to Al2O3 on aluminum. Aluminum has a self-passivating oxide Al2O3. Copper doesn't have something like that. Poor addition to dielectric materials such as SiO2. Poor addition to low-K polymers. So these are basically drawbacks. If we want to use copper as a interconnect, then we have to use diffusion barriers and adhesion promoters. What are these things? Let's understand. Use of diffusion barriers and adhesion promoters. Copper has poor adhesion properties and adhesive material is required which will provide stability across interface. Silicides such as TiSi2 can be used as adhesion promoter. TiSi2 does not have good barrier properties. So, to stop reaction between metals, that is tungsten, aluminum, etc. and silicon, or between two layers, a barrier layer is used. Titanium nitride has contact resistance higher barrier than TiSi2. Bilayer structure of TiSi2 and TiN is used as adhesion promoter and diffusion barrier. So this is diffusion barrier, this is TiSi2 and TiN. These are two material used. Since copper has poor adhesion properties, an adhesive material is required which will provide stability across interfaces. So TiSi2 can be used as adhesion promoter. This is adhesion promoter, TiSi2. And to stop reaction between metals and silicon, two layers, a barrier layer is used, that is TiN. So these two things required. Unlike aluminum metallization, copper cannot be easily patterned by reactive ion etching. To fabricate copper interconnects, a different process flow which is called Damascene process has been developing, including single Damascene and dual Damascene. We are done with this slide. We will move to the next slide. Single and dual Damascene process. Single versus dual Damascene process. Now let's see what are these two type of processes. There are two types of Damascene process. One is single and another one is dual Damascene. These are the method which is followed to deposit copper interconnect. So this is the first step. First ILD, that is interlayer dielectric or intermetal dielectric, is deposited and then that is etched to form the via. On that copper is filled, and in third step that extra copper is removed with the help of the process CMP, that is chemical mechanical polishing. Again, trench is etched in the deposited ILD. Here is via. Now trench is etched. That etched trench is filled with copper. That filling the trench with copper, and finally excess copper is removed using CMP. So that is single Damascene process. In case of dual Damascene, trench and via both are etched in the ILD at the same time, and that is filled with copper and excess copper is removed with CMP. So steps are less in dual Damascene process. So there less steps are required for dual Damascene. Now dual Damascene are two types. So one is via first and another is trench first. So in dual Damascene, both via and trench, these are done in same go. So if the via is first etched, that is called via first, then trench process, and if trench is first etched out, called trench first, via second. So this is the first one, via first process. So here we can see silicon wafer, in between that low-K dielectric is there, etched top layers are there, and resist layer is there. So this first via is etched out from here, then the trench. First via is etched, then trench is etched, and then TiN, titanium nitride layer is deposited, then seeding copper layer which is needed for electroplating of copper. In Damascene process, copper is deposited using electroplating. For that a seed layer is required. So that is done in this step. And then copper is deposited, and obviously after that CMP will get done to remove the excess copper. And in case of trench, first trench is etched away, trench and then via. So finally trench, via both are done, and titanium nitride is then seeding copper layer, and finally the area is covered with copper, and obviously excess copper will be removed by CMP process. So basically single and dual Damascene process, and these are the two different approach for dual Damascene. So we are done with this slide. We will move to the next slide. Aluminum interconnect versus copper interconnect. In case of aluminum interconnect, first on substrate aluminum is deposited, then this etching is done, or this aluminum is patterned so that dielectric can be deposited on that. So in case of aluminum interconnect, the substrate is coated with aluminium, which is then patterned using photolithography and plasma etching. Unnecessary aluminium is etched away, leaving behind the wires. The space between the freestanding wires was then filled with dielectric silicon dioxide. This is the step. In case of copper interconnect, the process is different. Copper doesn't form volatile compound with reactive gases, and therefore plasma etching is not used. So first a substrate is coated with a dielectric layer and trenches are formed by plasma etching. So first dielectric layer is deposited, then trenches are etched. Now copper is deposited by electroplating process. Excess copper is polished away. So dielectric etch, then copper fill, excess copper removal. This technology is known as Damascene because similarity with Damascene jewelry making. The dielectric must withstand mechanical stresses during CU removal polish. And low-K dielectric materials must also be able to survive thermal and mechanical stresses during the rest of the process step. All these high temperature processes related to copper, dielectric layer must withstand that. So from here we can understand requirements are there for low-K dielectric candidate, which is mechanically stable, which can handle these higher thermal cycles, which doesn't react in this high temperature and during these process steps. We are done with this slide. Now we will move to the next slide, low-K dielectric. Now we will try to understand what actually low-K dielectric is. Deposition of uniform, thin and porous low-K film is a challenging task. Another challenge is integration of film into IC manufacturing process. Low-K materials have disadvantages compared to silicon dioxide, such as they are mechanically weak, thermally unstable, poorly compatible with other materials, able to absorb chemicals, etc. From previous slide, we already know that when the copper and low-K dielectric is integrated in the IC manufacturing process, how copper interconnect are formed. A low-K material must have some properties. Mechanical strength should be there, it has to be thermally stable and should not react with other materials. These are the basic properties needed. Although generally low-K materials have this disadvantage compared to silicon dioxide, that they are mechanically weak, thermally unstable, poorly compatible with other materials, able to absorb chemicals, etc. What are the properties required for a low-K material? That is electrical, mechanical, thermal, chemical, general. These are 5 categories. So electrical, that dielectric constant must be less than 3. Breakdown voltage must be high. How breakdown voltage and dielectrics are related, if you want to understand this, please refer to the reliability episode. There I have discussed. Now low leakage current, that is leakage current and leakage related properties. In case of dielectric, that is also I have discussed in reliability episode. High reliability. So mechanical, what are the mechanical properties required? Good adhesion to metal or other dielectric, stability, that is low brittleness, crack resistance, and uniform thickness. Thermal properties, low thermal expansion or shrinkage required, high thermal stability required, high thermal conductivity required. Now chemical properties, no metal corrosion, it should not react with the metal, or in presence of this dielectric, the metal corrosion should be less than 1% moisture absorption, because most of the time low-K intermetal dielectric are porous. Moisture is present in air. Moisture or water particles can be absorbed by this material. They are very prone to that. So lower solubility in water, low defect density. General, environmentally safe, commercially available and low cost. Environmentally, that material should be safe, commercially must be available and cost should be less. So these are the properties required for low-K intermetal dielectric. Now lower K dielectrics are grouped as ultra low K, that is much less than 3, that is less than 2.2 to 2.4, or low K, that is between 2.4 to 3.5. These are called low K, and there are some ultra low also. These materials can be deposited either by spin-on route or spin-on dielectric or SODs, or by a chemical vapor deposition or plasma enhanced CVD technique. So their final properties are influenced by both the deposition method and post-deposition treatment, such as anneals or chemical treatment. So we are done with this slide. We will move to the next slide. Physics of low-K dielectric. Now dielectric constant K is also called relative permittivity. Permittivity, or K, is expressed as permittivity of a substance divided by permittivity of free space. A material having polar components has an increased dielectric constant. These polar chemical bonds are represented as electric type. Dielectric doesn't have free charges. That's why it's not a good conductor. Although its polar chemical bonds that is represented as electric dipole that actually contribute when voltage is applied, external electric field is applied, the dipoles align with the field and electric field of every dipole is added to the external field. So a capacitor with a dielectric medium of higher K will hold more electric charge at the same applied voltage. Therefore, C will be higher. So a capacitor with high dielectric medium of higher K will hold more electric charge. So its C or capacitance will be higher. This is the basic physics of dielectric. Now, how can we reduce the K? So two possible ways. One is reducing dipole strength, that is low polarizability. So if we reduce the dipole strength, that will result in lower polarizability. Another is reducing number of dipoles, that is lower density. These two methods can be combined to achieve even lower K values. We can combine these two methods also. Like silicon oxide, silicon and oxygen, this bond is replaced with less polar silicon fluorine, that is F fluorine, and silicon carbon, this bond. These are less polar bonds, SiF and CC, CH, SiC. These are the bonds. If we replace with that using virtually all non-polar bonds, that is CC-CH. Now, density of material can be reduced increasing free volume through rearranging the material structure or introducing porosity. If the material structure is rearranged, so that can change the porosity. Constitutive and subtractive. Two types of porosity are there. So, decreasing polarizability and decreasing density. There is a small mistake. It should be decreasing the density. If we reduce the dipole strength by changing the more polar bonds with less polar bonds, that will reduce the polarizability of the material. That way we can reduce the K. Another is if we decrease the density by increasing the porosity, that can reduce the K. So these are the methods how K or dielectric constant can be reduced. We are done with this slide. We will move to the next slide. Now let's know about different types of low K material. Constitutive porosity refers to self-organization of the material. After manufacturing, such a material is porous without any additional treatment. Subtractive porosity involves selective removal of part of the material. This can be achieved via an artificially added ingredient. If ingredient is added artificially, that is subtractive. Or constitutive is naturally like self-organization of the material. That is, as it is, without any additional treatment, the material is like that only. Now, classification of low K materials. One is silicon containing, another is non-silicon containing. Two types of silicon containing again, that is silica based and SSQ. That is silica based and SSQ based. To reduce the K value of silica, some oxygen atoms are replaced with fluorine, carbon or CH3. Addition of CH3 introduces less polar bonds and also creates additional free volume. The two, polarizability is also reduced and density is also free volume, that is porosity is added. Combination of two, that is also done. So the first low K materials were F or C doped, fluorine or carbon doped, SiO2. Now in SSQ, silicon and O atoms are arranged in a form of cube. This creates free volume in the center of the cube, decreasing the material's density K value. The cubes can be connected to each other through oxygen atoms. If some cube corners are terminated by hydrogen, it's called HSSQ, and ethyl group is at the corners, it's called MSSQ. These are some materials we have talked about. These are basically materials. This we all had about low K materials, copper interconnects and multilayer metallization. We are done with this slide, and actually we are done with our today's discussion. Thank you for staying up to this point. Don't forget to like, share and subscribe. If you have a dislike, please put it as a comment. And if you want to make any point, please put it as a comment. Thank you and bye for today.